So hello everyone. Today we will be talking about exact equations. Exact differential equations. So this video's purpose is to solve them. I will not be discussing about the theory behind the idea. But let's say we have a differential equation. Let's say we have dy dx is equal to a function of xy, and we can rewrite this in the form of two functions, which is m xy dx plus n xy dy. So the idea here is that we will be focusing on partial derivatives for this chapter, and the function of m and the function of n here, it presents the partial derivatives of the function of f, the big F we say. So let me rewrite this. We can rewrite this as d f xy. We could rewrite like that, and the function of m and n presents the partial derivative. So for m will be the partial derivative of the function f x of y, x of x, and then n represents as the partial derivative for f as well, but in respect of y. Before I continue, please do let me know if I said anything like wrong in a way, because it's this topic is very new and I would like to see whether my understanding is different than the rest of you. So now here is the idea. Now basically, if you can rewrite as this form right here, then we haven't determined whether it is an exact differential equation. There is this theorem where it called as test of exactness. This theorem helps us to determine whether the differential equation given is exact or not. And I believe that this only we'll be dealing only for first order differential equation, which is this one. And yeah, so now how do we determine whether a particular differential equation is exact? And what happens if it's not exact? Can we solve it still? But this video is only focusing on differential equations where it's exact from the get-go. And maybe some other time I might do a video about non-exact differential equations. So basically, let's if it satisfies this particular xy, if it satisfies this, when we take the partial derivative of y for the function of m, same goes if we take the partial derivative of x of x for the function of n, and if both of them are equal, then the differential equation is exact. Then what happens if it's not equal? Then we have some procedure that we have to do beforehand, and then we have to check again for exactness to solve it. So I'm gonna try and solve two questions. One is which that it don't give us the initial value problem, IVP for short. Yeah, the first one will be for a general solution, and the second will be a particular solution given the values. So let's try. Okay. The questions that I'll be solving is from my tutorial questions. So, alright, let's try I'll try to solve one. So this is the only thing that we have to remember. The theorem. Well, I'm not going to write down the theorem, but basically, if this satisfies, then the differential equation is exact. So let's start with a simple problem. I believe that question 4a, or in my tutorial here, question 4a will be, it's a very simple problem. We have this differential equation given that we have y dx plus x dy, I believe. So first things first is that we have to determine which one will be the function of m. and which one will be the function of n. So by referring to this general form, the sum for partial derivatives, so basically this is our function of m and this is our function of n. Right, so you have determined the function of m and n. Now you have to take the partial derivative for each function. So for function of m, you will be differentiated partially only for y, meaning that any x terms you will be dealing it as a constant in a way. So the partial derivative in respect of y for the function of m will be 1. Same goes if we take the partial derivative in respect of x for function n, it will be 1 as well. So what does this mean? This means that since both of them are equal, and by the theorem itself, the differential equation given is exact. So since this similar to this, then the differential equation, DE stands for a differential equation, is exact. So now, what are we going to do? We can solve it. Very nice. And heads up, you could solve this in a, you could separate them. Okay, I believe you could separate this. You could solve it. That will be much more better. Now I'll be showing you how to solve using exact equations, right? But there are some cases where if the differential equation is exact, it doesn't mean that we can solve it by using the separable variable. Okay, only a few situations. But for this, you could solve it by using separable variable and you integrate one at a time. But now let's try solve this. So first, to solve it, we have to integrate the function of m in respect of x. So in other words, we will do it like this: df dx as I recall. Let us recall a bit. So this is similar to function of m. That's basically what I'm trying to do right now. So by integrating it, we'll integrate the function of m. And now when we integrate the partial derivative, the left hand side there, we will have f. So in other words, when you integrate, it's the same as when you differentiate partially. You treat one term and then you treat the other term as a constant. So in this situation, we will treat y as a constant. So for function of m, y, the term y is constant. Therefore, from here, it's just basically you will integrate. You will have the variable for the d. Since here d is x, then when you integrate y, then you have xy. So yeah, you'll be adding with a function, and this function is a constant function in a way. So g of y. Now I believe that if you integrate dy, meaning that you integrate the function of n, then your constant function here will be g of x. It depends on which one you choose, because at the end of the day, it justifies. It's just meaning that you integrate respect of x, and then you differentiate partially respect of y. So let's say if you choose function of n, you integrate function of n respect of y, then you differentiate partially respect of x. Theoretically speaking, you will obtain the same thing. Yeah, I'll try it after this. Anyway, after you obtain this function of f, then you differentiate it partially respect of y, just so you can like get rid of this constant function. You can compare with it, because as we recall, the partial derivative of f respect of y is the same as the function of n. So when you take the partial derivative in respect of y here, then you will have x plus g prime of y. Okay, and then g prime of y, you could compare it with the function of n. So we know our function of n is only x. Then when you see here, when you compare, it's 0. You're comparing with a term 0. So you will have g prime of y is equal to 0. So when you integrate both sides in respect of y, then you will have g of y is equal to c. Okay, 0 is a, well, 0 is a you differentiate a constant, you will get a constant. So that's the idea, and hopefully it's a nice idea to begin with. Anyway, oh yeah, when you asked me, right? So when you integrate 0, you get 0 times y, which means 0 again. But this is an indefinite integral, so it will be 0 times y plus c. That's basically about it. And when you differentiate this, you obtain 0 again, so doesn't matter. Anyway, you obtain your g, the function, the constant function, which is g of y. Then you go back to your original function of f. Then just substitute it. You will get the value, which is xy plus c. Now, this is not a solution. This is just a function, generally. So what will be the solution? So the solution will be xy plus c is equal to 0. And then we know that when you take away c both sides, you will have negative c. But we argue that negative c is still a constant no matter what. So xy will be c as well. Or if you want to change the variable to an a, you may, but you have to mention on your right hand side that you've substitute negative c with a as a new constant. So honestly, that is just about it, and very nice indeed. Okay, so like I said, I want to try, I never tried this before. Let me try and integrate this in respect of y first, and then I differentiate partially respect of y, sorry, respect of x. So let's say df dy is equal to, you integrate the function of n in respect of y, then go back here, your function of n will be x, so basically integrate a constant, you will have xy plus g of x. So f is equal to xy plus g of x, and when you partially differentiate this in respect of x, therefore you will obtain, well, y plus g prime of x. Now this, just refer back to your function of m, which is y, therefore it's the same thing. Okay, x dx is equal to 0 dx, and the constant function, which is g of x, will be c. And then as usual, the function of f will be xy plus c, but the solution will be xy is equal to c. Alright, I'm gonna skip a few steps for this part because it's the same thing. So basically, right, it doesn't matter which one you want to start integrating, as long as you just change the steps. Like if you integrate in respect of y, then you differentiate partially in respect of x, and vice versa. So that is very cool, a cool one. So yeah, it's very easy, and you could solve this as well using separate variable. Let me try that just a bit. So I could separate this to become negative 1 over x dx is equal to 1 over y dy. You integrate both sides, you have negative ln the absolute value of x is equal to ln absolute value of y. Then just raise both 1 over x y. Oh yeah, I forgot a constant. Damn it, forgot a constant. Here you go. So you're left with 1 plus x, and there is c ln absolute value of y. And now you can get rid of the absolute value. Well, since both of them are having an absolute value, you can get rid of it instantly, because it doesn't matter because if both sides are positive and both sides are negative, then it will cancel out one another. So you are left with 1 over x is equal to e raised to power c y. And yeah, you get xy is equal to 1 over e power c. This is still a constant, so you get c. right? So yeah, you could solve this using subvariable. Very nice indeed. Okay, so I'll show you a lot of ways to solve this. Hopefully my explanation is correct. If not, then just let me know. Okay, let's try solve one more, and I'll call it a day. Um, I believe that question. Okay, this question, the initial value problem. First, we had to solve the differential equation. Then we had to find a constant based on the initial values given. Okay, this will be my last one. So question B, we have this differential equation. Oh, sorry. 1 minus 1 square dx plus 2x cubed 1 minus 1 dy. Sorry. This is equal to 0. And the initial values they give is y negative 2 is equal to 5 over 2. So those are our initial values. And okay, first things first, determine the function of m and function of n. The second step is using the term of exactness. If they are equal, that is the differential equation is exact. Then the third step, you either can integrate in respect of x or y, doesn't matter. And then the fourth step is you differentiate the opposite variable, meaning that if you begin with integrating in respect of x, then you should differentiate partially in respect of y and vice versa. And then solve for the constant function, replace back in your original function, and from there you obtain your solution for the function, and then you could obtain a solution by equaling to a constant. Okay, so that's a lot to take in. So let's try and apply those steps. So first we have to determine whether the differential equation is exact or not. So we will differentiate partially for the function of m. So we will obtain this. So 3x squared y minus 1 squared. So 3x squared we did it as a constant, so don't need to use the product rule to differentiate. Waste of time. Now by using the power rule for this and then chain rule as well, you have 6x squared times with y minus 1. Same goes for the function of n. Function of n, you differentiate partially in respect of x. You will have 2x cubed times y minus 1 dy, y, 2x squared times y minus 1. You differentiate partially in respect of x, therefore you will have 6x squared times y minus 1. So from here, since both of them are equal, therefore this differential equation is an exact differential equation. Okay, very nice. And that's the first step. The second step is by, well, you have to solve for m. So by finding the integral, whether you want to begin with m or n, either functions is, there should be no problem. Okay, but I'm gonna approach it as usual in respect of x. So we integrate this in respect of x. So we integrate the function of m. Now we have f is equal to, the function of m will be 3x squared y minus 1 squared. So this implies that, well, we will be treating y minus 1 squared as a constant. So we will obtain this. I'm just going to skip a few steps here. Straight to the answer, g of y. And now by differentiating partially respect of y, therefore it will be 2x cubed times y minus 1 plus g prime of y. And by comparing it with function of n, which is this function here, therefore g prime of y is a constant, so we will have like this. So by integrate this respect of y, therefore you will have c. And then by substituting back into your original function of f, you will obtain the function of f, which is x cubed 1 square plus c. And then the solution will be x cubed y minus 1 squared is equal to c, or negative c, but still a constant, therefore we leave it as c. And since this is an initial value problem, IVP, we have to use the given initial values, which is y of negative 2, 5 over 2. So the way you want to read this is that inside of the parentheses is the x value, and then out here the output will be the y value. So negative 2 to the power 3, 5 minus 2, 5 over 2 minus 1 squared equals c. This implies that negative 8 times with 9 over 4, if I'm not mistaken, 9 over 4, so you have negative 18. I'll check it later. So your final answer will be x cubed times 4 minus 1 squared is equal to negative 18. Is it negative 18? Not really sure. So question 5. Oh yeah, so that is the final answer. That's the solution. Okay, so it's simple to say that exact differential equation, if you already determine but the get-go, you don't need to do other steps to convert into an exact differential equation. But maybe later on I'll be making a video about non-exact differential equations and how to convert those into exact differential equations. Okay, so that's about it. If there isn't, I have nothing else to say. But if my explanation is a bit off, please do let me know. I'll try to improve it in the next video, or I'll let you guys know. Okay, so that's all for now. Thank you so much and have a great day.